On this video, we're going to do some practice problems to prepare for the Chapter 11 test. So if you, at any point in time, want to just pause this and try the problem yourself, and then you can listen to how I do it and see if that makes sense. So the first one we're going to do is I'm asking you to draw, if possible, the graph of a cubic polynomial, and then I've got A, B, C, D. Can you draw a cubic polynomial that has no real zeros? Can you draw one that has exactly one real zero, one with two, and then one with three? So on the first one, part A, it is actually not possible. So what we see is that the end behavior in a cubic polynomial, and so by cubic polynomial I mean something that has an x to the third in it. So whatever else it may have, so if you have something x to the third plus whatever other smaller powers of x, our leading coefficient test says that the end behavior is determined by the highest power and its coefficient. So if you put in a large positive number, then if A is positive, the right end behavior will be positive. And if you put in a large negative and you have a positive coefficient, the left end behavior is going to be negative. If the A is negative, it will be reversed. It'll be positive to the left and negative to the right. But either way, it's going to come and go in different directions, are the words I would use. And so whatever else that polynomial is going to do, it's going to have to cross the x-axis somewhere. And where it crosses the x-axis represents a real zero. So it's not possible to draw a cubic polynomial that doesn't cross the x-axis. So part B, you can certainly do that. You could do something that does something like that. You could also, if you like, imagine it does something like this. Remember, a cubic could have at most n minus 1 or 2 turns, so it could do something like that. Or, you might recognize this as being the cubic polynomial y equals x to the third. For part C, to have two zeros, that is possible. You could do that probably a couple of ways. You could have one that is going to cross and then bounce off of the x-axis. So that's representing a zero that has multiplicity 2, but it's only going to have two distinct real zeros. I should maybe have made that clear. Okay, and finally, part D, it is possible to have a cubic polynomial with three zeros. It could do something like this, where we have a cross, cross, cross. Okay, new question. I'm going to give you a graph, y equal, or I'll give you a polynomial equation, 2x minus 1 to the third, x plus 2 to the second, times 3x plus 5, and finally times a 5x plus 2. And I'm going to ask you several questions about this. Can you find the degree of that polynomial? Can you find what is its leading coefficient? And similarly, can you find what is the constant for that polynomial? What's the number that has no power of x at all? So the degree, we can see that if you multiply this all out, which we don't want to do, out of this term we're going to get something to the third power times something to the second power times something to the first power times something to the first. We'll add those exponents, and so the degree is going to be 3 plus 2 plus 1 plus 1, so that is going to be a degree 7 polynomial. For the leading coefficient, out of this term, we are going to get a 2x to the third power. So among other things, the highest power of x that's going to emerge out of this term is going to be an 8x to the third. The highest power of x that's going to come out of this term is an x to the second. And from here, we'll get a 3x, and from here, a 5x. So eventually, these are all going to multiply each other, And so what we're going to end up getting is, here you can see again our x to the 7th term, and the coefficient is going to be an 8 times 1 times 3. So it's going to be an 8 times 1 times 3 times 5. And so 8 times 5 is 40. 40 times 3 is 120. So the leading coefficient is going to be 120. In a similar fashion, the constant is going to come from, out of this term, we're going to get a negative 1 to the 3rd. And out of this term here, we're going to get a 2 to the 2nd. And then we're going to get a times 5. And then we're going to get a times 2. And so those are going to all multiply each other to give us the constant. And so the negative 1 to the 3rd is negative 1. I guess 2, I'm going to go this way. 2 times 5 is 10. Times 4 is going to be 40. So our constant is going to be a negative 40. Okay, another question for you. This is a true-false question. These are kind of tough. And I want true, false, and then explain your answer. And so the explaining is as important as, maybe more important than the true, false part. So I'm going to say, it is possible. So here's the statement that I want to know, is it true or false? It is possible for the complex conjugate of a number, the complex conjugate of a number, to equal the opposite of the number. The opposite of the number. So here you can show this is true if it is possible by giving an example of one. So remember, a complex conjugate, if we're talking about now complex numbers, so something in the form a plus bi, where a and b are real numbers. So a and b can be any real number, and that could include 0. So the complex conjugate is, remember, we write that as a plus bi with a bar over it, and that is a minus bi. So you leave the real part the same as it was, and you change the sign of the imaginary part. The opposite of a number is the negative of that, which means it's going to be the opposite of a and the opposite of b. So the first one is the conjugate. The second one here is the opposite. Now, is it possible for these to actually equal each other? And at first glance, you might think that isn't possible. But I would argue that, I left off the negative on that, so they're conjugate. So the only way that could be true, so no matter what you plug in for the b, we're going to be okay, right? These are going to be the same thing. The question is, how in the world could a be equal to negative a? What can we ever make a equal to negative a? And of course, the only way that's true is if a is 0. So what that's saying is that if we choose a complex number a plus bi, where the a is 0, that is, if we pick something that is purely imaginary, for example, we could say, what if we chose 5i? Well, let's see, the conjugate of 5i would be, because you could think of that as being 0 plus 5i, its conjugate would be 0 minus 5i. And so here is a case where the conjugate is indeed exactly the opposite of the original. So that is actually true. And you can give an example of any pure imaginary number would be evidence of that, would be an example of that. So let's try another true-false question and explain again, and see if we can see how the game is played. So the statement is a cubic polynomial with integer coefficients A cubic polynomial with integer coefficients can have zeros, can have as its zeros, we'll say 3i and 1 minus 2i. Now, at first glance, you may say, well, the fundamental theorem of calculus says that a cubic polynomial, which means degree 3, can have 3 zeros. So surely 3i and 1 minus 2i could be 2 of the 3 zeros. But what this is trying to get you to think about is our complex conjugate pair theorem, which says that if we have real number coefficients, and integers are certainly real numbers, then if 3i is a 0, its conjugate must also be a 0. And likewise, if 1 minus 2i is a 0, then 1 plus 2i would have to be a 0. So now we're up to 4 zeros, and so a cubic polynomial, a degree 3, cannot have 4 zeros. We'd need at least a 4th degree, and so this is actually false. Okay, let's try another example here. We're going to divide. So let's see if we can do some long division. We're going to divide the polynomial 2x to the 4th. I'm just going to write it in a more friendly form. So I'm going to say 2x to the 4th minus 3x squared minus 3x cubed. Let me make that a cubed. And then minus 2x squared plus 5x plus 7. We got all the powers represented, so I don't need to fill in with any zeros. And we're going to divide this by a quadratic, x squared minus 2x minus 3. So I'm going to force you then to use long division. You can't try to get around this, not in a very good way anyway, certainly, by doing synthetic division. So we're asking ourselves, what times x squared is 2x to the 4th, and that will be a 2x squared. We'll multiply the 2x squared times the divisor, so 2x squared times x squared is 2x to the 4th. 2x squared times a negative 2x will be a minus 4x to the 3rd. 2x squared times the minus 3 will be a minus 6x squared. We're going to subtract that quantity, so the 2x to the 4th minus 2x to the 4th drops out. The negative 3x to the 3rd minus a negative 4 becomes a plus 4x to the 3rd, so we're going to get an x to the 3rd down below here. Negative 2x squared minus a negative 6x squared is going to be a plus 6, so that'll be a plus 4x squared, and then the 5x and the 7 will come down. So we reload here, and so now we're going to ask what up here times x squared will be x to the 3rd, and that's going to be an x. So x times the x squared will be x to the 3rd. X times the negative 2x will be a negative 2x to the 2nd. X times negative 3 is going to be a minus 6x. We're going to subtract that quantity, so the x cubes will drop out. 4x squared minus negative 2 makes it a plus 2, so that's 6x squared. 5x minus a negative 6x makes that a plus 6x, so that's going to be 11x and then plus 7. We'll do it again. So now we're saying what times x squared is 6x squared, so that's going to be a plus 6. And we'll get a 6x squared here. 6 times a negative 2x is a negative 12x. 6 times a negative 3 is a negative 18. We're going to subtract that quantity. And so that is going to, we'll get rid of the x squareds. 11 minus a negative 12 becomes a plus 12 is 23x. And 7 minus a negative 18 will make that a 25. The degree here is now degree 1. Our divisor was a degree 2, so we are finished. So we can write our answer in one of two ways. We can say either the polynomial, the original p of x, divided by x squared minus 2x minus 3 is the quotient 2x squared plus x plus 6, and then plus take our remainder, 23x plus 25 over what we divided by, the x squared minus 2x minus 3 as a fraction, or we could write it as p of x is equal to the divisor x squared minus 2x minus 3 times the quotient 2x squared plus x plus 6, and then plus the remainder, the 23x plus 25. Either of those answers is okay. All right, let's try another example. I'm going to give you a polynomial, p of x, and I'm going to tell you that is 3x to the fourth minus x squared minus 4x plus 6. And I'm going to tell you to evaluate, that is to find p of 2 different ways. So the two different ways we have, the first way is our old inefficient brute force method where we just plug in 2 everywhere we see an x. So that's going to be 3 times 2 to the fourth minus 2 to the second minus 4 times 2 plus 6. So that means we're going to get, let's see, 2 to the fourth is 16 times 3 is 48. 2 squared is 4, so that's going to be a minus 4, a minus 8, and a plus 6. And so I guess the negative 12 from the negative 4 and negative 8 will make the 48 into 36, plus another 6 is going to be 42. So that's one way of getting our answers. Our more efficient way, the new way we have learned, is what we call synthetic substitution, where we're going to do all the stuff that we did for synthetic division. Oops, did I say it was a squared? So I need a 0 where the cube is. So I'm going to do all the things that we did for synthetic division, but I'm only going to use the number we get at the very end, and that's going to be our p of 2. So the 3 comes down below the line, then gets multiplied by 2 and becomes 6. We add 0. We multiply by 2 again. We add the negative 1. We multiply by 2. We add the negative 4. We multiply by 2. And we also get 42. So the 42s we get are the same either way. That's good news because we should get the same thing. Okay, let's try a new one. We're going to graph here y equals 3x squared times 2 minus x to the third times x plus 3. So we're going to find our zeros and use the cross bounce swirl rules that we talked about. This has a little bit of a twist in it that you're going to have to notice. We'll get to that in a moment. So the zeros are going to be what makes these equal to 0. So 3x squared will be 0 when x is 0. So we're going to get an x-intercept at 0. 2 minus x is going to be 0 when x is 2. So that's going to be another 0. And x plus 3 will be 0 when x is negative 3. So we're going to get another x-intercept at negative 3. So we have x-intercepts at negative 3, 0, and 2. I'm going to look at the left-end behavior, and I'm going to do that by looking at what happens here as x goes to infinity. And actually, I'm going to look at the left end, so when x goes to negative infinity. So if I put a very large negative number in for the x, it's going to get squared, multiplied by positive 3. That's going to be a positive. Now here's the tricky part, the sneaky part. Because it's 2 minus x, when I put in a large negative for x, we're going to get 2 minus a negative is actually going to be a positive number to the third. That's actually going to be positive. And a large negative plus 3 will be negative, and the product of a positive, negative is going to be negative. So it's going to go to negative infinity. That means the left-end behavior is going to come from below, from the negative. So I'm going to say the left-end behavior is here. I'm going to do that in a little bit different color so you can see it separate from the actual intercepts. So it's going to the negative. Now, as we approach that -3, that came from this factor, which was to the first, so we're going to just cross as we come up there. When we get to the 0, that came from the x squared. Since that's an even power, we're going to have to bounce as we come off of there. And when we get to the 2, that came from the third power, so I'm going to have to swirl as we go through there. And so that's going to be our graph. Okay, I'll try another problem, a different kind of problem here. So I'm going to ask the question here, is -2 plus the square root of 3 a 0 of the polynomial 3x to the third plus 10x to the second minus 5x minus 2. Now there are several ways you can do this, and part of this you're gonna have to kind of make a choice which you think is the easiest or the most efficient way, and not everybody always thinks it's the same. So first way we could do that is I could just brute force that and plug it in everywhere we see an x. I don't think anybody's going to really like this one, because you're going to have to take that -2 plus square root of 3 times itself 3 times, and that's kind of daunting. And then you're going to have to do it times itself twice, and so on. Some people might try to do synthetic division or synthetic substitution. I'm going to show you this way. I'm not sure you're really going to like this. I think the last way that I'm going to do it is probably the way most people will do it, but I'm not going to say necessarily everybody will like that. So if we do it using synthetic substitution, the question we're going to look for is, what is this number there? If that turns out to be a 0, then we will answer this question yes. And if that's not 0, then we'll answer the question no. So starts out easy enough. The 3 comes down, and now it starts to get ugly, but it's going to get a lot worse. So I'm going to distribute that 3, so that's going to be a -6 plus 3 square root of 3. I'm going to add down, so the 10 and the -6 are going to make that 4 plus 3 square root of 3. And now here's where it's not much fun anymore. We're going to have to multiply these out. And so let's see what we get. -2 times 4 is -8. -2 times 3 square root of 3 is a -6 square root of 3. Square root of 3 times 4 is a +4 square root of 3. Square root of 3 times 3 square root of 3 is going to be 3 times 3 is a 9. So that -8 and 9 are going to make that 1. The -6 square root of 3 and the 4 square root of 3 make that a -2 square root of 3. Yuck. So that's 1 minus 2 square root of 3. Okay, slogging on, we're going to add these together. So now we have -4 minus 2 square root of 3. Now we're going to have to do this again. So here is our -2 plus square root of 3. If you're really paying attention, you might see why this might have a hope of being something fairly nice. If we multiply that out, the -2 times -4 is 8. The -2 times -2 square root of 3 is a +4 square root of 3. Now good things happen. Square root of 3 times -4 is a -4 square root of 3. Look at that. Those things are going to cancel each other. Square root of 3 times a -2 square root of 3. The square root of 3 times square root of 3 is 3 times -2 is a -6. And so these are going to cancel each other out, and we're going to get just a 2. And how about that? What a carefully constructed problem. The answer is yes, that is actually a 0. Let me show you another way of doing this that I think a lot of people are going to like a little bit better. You can be the judge. So if we know from our complex conjugate theorem that if -2 plus square root of 3 is a 0, and these are all very nice coefficients, that is, you don't see any square root of 3's in there, then that means that -2 minus the square root of 3 is also going to be a 0. It's conjugate, not complex conjugate, but just conjugate, the thing that will make that the difference of two squares. So if this is a 0, then x minus that will be a factor. So that is one factor is going to be x plus 2 plus square root of 3. That's from this one. And a second factor is going to be x plus 2 minus the square root of 3. So what I'm proposing is that we multiply these out. We're going to get a quadratic, and then long divide the quadratic into the original and see if that gives us a 0. If it does, then both of these are zeros. If it doesn't, then they aren't. So we're going to do a little bit more work up front than maybe we did with the synthetic division, but I think at the end, when you see our long division, it'll be somewhat nicer. So here we are again using our strategy of thinking of that as a plus b and that as a minus b. So we're going to get the difference of two squares. So we're going to get a squared minus the b squared is going to be just 3. So that's going to be x squared twice the product is 4x plus the second one squared is 4 minus the 3. So that's going to be an x squared plus 4x plus 1. Now, if we can long divide this into our original polynomial, then if this has 0 for a remainder, then both the negative 2 plus square root of 3 and the negative 2 minus square root of 3 are zeros, and if not, then they aren't. So let's see, I got 3x to the third, I've got a plus 10x to the second, minus 5x, and a minus 2. So I'm asking what times x squared is 3x cubed. That's going to be a 3x. So here's 3x to the third. 3x times 4x is a 12x squared. And 3x times 1 is a plus 3x. I'm going to subtract these. The 3x cubes drop out. 10x squared minus 12x squared is a negative 2x squared. Negative 5 minus the 3 is a negative 8x, and the minus 2 comes down. And so then I'm saying what times the x squared will be a negative 2x squared. I'm going to go on minus 2. Here's a minus 2x squared. Negative 2 times 4. Oh, look at that. It's a negative 8x. Negative 2 times the 1. Oh, can you believe it? Sure enough, these are going to all be 0. Since we get 0 for remainder, then doing it this way, we can also conclude that, yes, negative 2 plus square root of 3 is a 0. I think those are going to be your two best bets. You can see if you like any of those better. I'm going to stop this here. I'm going to do another one with a few maybe different problems.